Hello, everyone. We'll start briefly. Hello. Before we start, I will make some announcement and make the introduction. So can you guys hear me? Dr. Jaran? Okay, good.
Yeah, we can hear you.
Okay, make sure you guys all good. Okay. So this is a follow-up program, the second one, follow-up program to conference, AI Healthcare Conference. We organized. Someone says they cannot hear. I guess you can hear Dr. John.
We can hear you.
Okay, perfect. So this is a follow-up to AI Healthcare Conference. We had a fantastic AI Healthcare Conference at Stanford. And since people were tired at the end of the day for the workshops, so we decided to extend the workshops to another day. And we see that a lot of people are available to join today. And hope that you guys benefit and maybe get intro to more AI in medicine with this one. So my name is Murat. I'm Stanford scientist and serial entrepreneur and co-founder of Magnimind Academy along with Dr. Jaran. We've been organizing these programs and meetup groups actually past 5 to 6 years. We have so many meetup groups. If you're not a member of those meetup groups, you're welcome to join them. Where you're gonna learn actually our events. First time we announce on those meetup groups. We organize around 300 events. And then it is lectures, workshops, small AI events, panels. We have so many events. You're welcome to join and register there. We have YouTube channel. We put our recordings on our YouTube channel. It's very rich content. If you want to learn the different areas and interest in data science and AI, because our YouTube channel is a good place to be subscribed. And our other social media platforms, each one we have different content we post. Our goal to enrich the community of Magnimind in data science and AI. We have actually reached over 30,000 people in our meetup groups and members. So there are a few program announcements starting soon. We have mentorship/internship programs for people who have studied data science, but not able to have a chance to do projects and not have a chance to get an experience. So we provide students 4 to 5 mentors, is one-on-one base. And then students get to work with our affiliate companies. They do projects together with engineers where they grow and build themselves. We have actually a special track there in AI in medicine track where we have the most strength as a Magnimind Academy. So you will be able to get in that track as well. And then there's a special coupon code. Our team has put it in the chat. You may use that. There's a limited time for that. If you need to learn more information, you can just let us know. So we have also mini boot camps you can register, especially one and just follow up to this one in 8 with Dr. Jaran is gonna give AI in medicine mini boot camp. This is more on lecture based. It goes above and beyond these topics. And we have another one in LLM. These are the 8 weeks boot camps. It's not 101, it is with a group, but there's nothing similar you will find. You can just register those meetup mini boot camps as well. So I will introduce Dr. Jaran. Most of you knew it last week. He's again co-founder of Magnimind Academy. We've been working together on years. We also work on several projects with the Stanford University, especially in medicine and healthcare together. He's currently faculty in San Jose State University. And prior to that, he was in Santa Clara University faculty and KAIST University in Korea faculty. So he has 20 years plus experience in this field, and is one of the best faculty person you can get this workshop from. So Dr. Jaran, when you're available, you're welcome to start.
Thank you very much, Dr. Vaday. Thank you for introduction. Hello, everyone. Welcome to the second workshop on developing a predictive model for sarcopenia. I'm going to share my screen, and I'm going to also share the material which we're going to use. Again, last week, if you attended last week, you already should have the material, but if not, no worries. So I'm going to give you the material. So before we get started, so this was a small introductory presentation I prepared for the conference at the time, but again, the time was so limited, I couldn't even find an opportunity to tell what this project was about. So this project that we started last week, working on this project, is about detecting sarcopenia. What is sarcopenia? It's a skeletal muscle disorder. And then there are certain characteristics of this disorder. The important one is loss of muscle mass and strength. Right? So what is the effective diagnostic? Why is it so crucial? Effective diagnostic system. First of all, we want to prevent and treat fast. Increase the stop the progression, right, of the disease, and then we want to reduce healthcare costs. So, these two are the most important factors. Okay. So right now, what happens is there are certain tests patients are going through when they go to a clinic or a hospital, actually. So the metric that researchers and maybe doctors are using, one of the metrics which is also in the literature published widely, is taking the ultrasound image of anterior thigh. So they are actually measuring the muscle thickness by looking at this ultrasound image. So right now I'm working on this ultrasound images. So I'm just continuing working on this project. So I'm working on those images now. But what happens is after measuring the thickness of the muscle by looking at the ultrasound image, so they're dividing that thickness by the BMI of the person, they get some metric called star. And then if the star is less than 1.0 for female or less than 1.4 for male, they diagnose the patient with sarcopenia. Okay, so this is how the current workflow is running. And in addition to this muscle thickness, traditionally, again, what doctors do is they ask patients to go through a simple chair stand test. So a chair stand test is patient is sitting and then standing up 5 times on a chair, and then the physician or the nurse is taking the time and then measuring the time, how long it takes for the person actually properly sit and stand up on a chair. Another very widely used test is this hand grip strength. Okay, so there are certain very simple devices where the patient is asked to, as much as she or he can, hold the fist really tight on this, holding this device, and then they're measuring the grip strength. So the current workflow is, let me make this a little bit bigger. So when a patient arrives, So they first find the age of the person, depending on the age of the person. If the person is greater than 65, then they are looking at their grip strength. If grip strength is normal, so grip strength and chair strength test, they are looking at these tests. If these two are normal, so they say there is no sarcopenia. If these tests are not normal, so they call it probable sarcopenia. And then they run through the, what is that, ultrasound image. Again, with the ultrasound image, if the star rating is low, then they say it is sarcopenia. If star rating is coming high, that means there isn't apparent problem with the muscles, but still the patient is not sitting, is not passing chair stand test or grip strength test. That may bring some problems, some mental issue problems, which patient is asked to take some further tests. So this is the current workflow. So what we want to do is we want to actually reduce number of patients going through this ultrasound measurement. So we want to detect as many as possible here from the patients. Another thing is there are patients, again, according to data, we have a really relatively large data set in this context, not too large, but relatively large data set from many different hospitals and countries, actually. And then what we observe is patients who are younger than 65, in this case, even younger than 50. Even though this workflow is not making sarcopenia diagnostics, the ultrasound images are showing significant muscle loss. So then again, we are trying to see if we can develop a model which is going to even detect those patients. So that is an ongoing project. So that's what I wanted to look at with you. So let me get to where we left last time. Again, I'm going to share the GitHub link with you so that you can find the data. Again, this is just sample data. So you can, oh no, this is another workshop. I'm sorry. This is the medical image workshop. This is the workshop. Yeah, so you can find the sample data sets as well as a cleaned data set, and then the models that we created, and then the workshop files. Okay, so I'm going to share this link with you. I just wanted to give you a background on, so you're not seeing the screen fully as of now? Can you not see my screen? So I just received the...
No, we can't see your screen. I guess that one person.
All right. Okay. So I'm sending the link to the GitHub account from chat. All right. So here is the link. Okay, Yukta, thanks. Here is the link to the GitHub account. Again, you can get all the material from here. Okay, let's continue. Remember from last week, what we did was we tried to clean the data set, and it took longer than I actually expected. So again, we need to run some of that code right now together. If you guys already have this file in front of you, we need to run this file and then make the data ready. So again, I'm loading. So this is student version. Okay, this is the file I was working on last time. I'm going to read the data set. Okay. So the data set is read, and then it is now on this platform. Let me get rid of this left panel so you can see my code. Okay. And then what we did was we checked the data set size. We had around 1,500 data points, and then with 41 columns. And these were the column names. I'm not going to run this. It's not essential. And then what we did was we removed some empty spaces around the column names. That was part of the preprocessing. That was just a case. I just wanted to share with you that you need to do some extra stuff that you didn't even think about when you begin dealing with the data sets. And then here you can see some of the columns are actually having a lot of missing values. That was the purpose of this .info. Again, I'm just moving fast here because we already did this part with you last week. And then I'm only selecting a certain number of columns, okay? So I'm going to focus on these columns. The reason is the experts on the field, right? The people who know this context a lot deeper, more than me. They already did a lot of research on that. They said, let's focus on these variables. I said, okay, of course. Now, these are the new columns. So I just narrowed my data down into these columns. And then what I did was, next was, I just looked at how many unique values in each column. So that will help us identify which of these columns should be treated as categorical variable. Remember that, for example, grip strength has 56 different values. That means it's not a categorical value. Most likely it is a continuous and numeric value. But if you look at what is that, HT, right, or DM, right? So these are, or smoking, maybe education. So these are, or exercise. These are categorical variables. And then for the education, we saw that there are many different categories. Some of them may mean the same thing, even in a different language. So that's another thing I wanted to share with you at the time. So you need to really sit down and then look in detail to your data set and then see if there are things that you need to take care of. In this case, for example, we needed to take care of the missing values. And for this case, I just dropped all the rows with the missing values, which may not be the ideal case. We are just simplifying this whole process. I just dropped all the missing values with this line here, okay? And then after dropping the missing values, as you see, my data set reduced from 1,500 to 1,132 data points, okay? And then what I did was I changed some of the column names. For example, grip strength was changed to HGS because of the way in the literature this test was called. It is called HGS, so I'm using HGS. And sarcopenia, I just reduced it to SIRC. So here I just wanted to let you know how you can change the column names. And then next, what I did was, remember, I mapped the categorical variables like exercise, education, to numbers. And these numbers are actually, again, the category. So, for example, illiterate is category 0, or primary school is category 1. So that's what I did in here. Or exercise, not doing exercises, category 0. Doing exercise only 1 or 2 times a week is category 1. Okay, so we created these categories so that later we are going to use categories to create codes for each category. All right, and then I also did the same thing for gender. And here is my final data set where I have now all my columns without any missing value. You have to be careful. Even though this says there isn't any missing value among all data points you have, there might be some not very meaningful data points, which is entered by mistake. For example, for age, if the number is like 300, right? So how can you find someone with 300 years old, right? So it's wrong. But still, let's go with this. Right now, we see that there is no missing value. But again, this doesn't guarantee that we don't have any missing value. And then I also do some data type parsing here. Again, please refer to the recording from last week. I'm just going through what we did very quickly, what we did last week. And this is how our data set now looks like. So as you see, here is age, gender. So I already encoded this into 0, 1. Exercise, I encoded exercise like 1 or 2 times a week into, let's say, 1. More than 2 times is encoded into 2. So here is our data set, looks like how it looks like this. SIRC is our target variable. This star is the golden rule the doctors were using. So in my model, I'm going to exclude this one, because if I know the star rule, if I know the star score, which is coming from ultrasound images, I don't need anything else here, because by just looking at star, I can make the diagnosis, right? If star score is less than 1.0 for female, then it is sarcopenia, right? So that's why I'm not going to use star in my predictive model. Okay, now we are almost ready. One more thing is we looked at the description of our data set just to see if there are any not meaningful data points. For example, age, I'm just checking if the maximum is meaningful. 92 it makes sense. If it was 292, then it doesn't make sense. I need to go back and then check that data point, right? All right. Okay, and then finally what I did was I added a new column called ID, because when I received the data set, I already removed, or they already removed all the ID related information for privacy issues, right? From the data sets here, I just assigned the index value of each row as the ID column for my data points. In this exercise, we're not going to use ID, but when you continue working on this project, you may need ID numbers to identify the patients. I keep repeating saying customers, so in case I say customer, I'm referring to patients. All right, the rest of this section was about looking at how different variables are distributed when you group your data by gender. And then we saw that there is some serious differences in terms of gender, male and female. So that's why it made us think that maybe we can develop two models, one for female and one for male. And this is where we left last time. Okay, so this is where we are now. So let me see if there are any questions, anything. Yeah, so again, if you guys are already registered, you should receive the recording from last week. Probably, oh, they already gave you the YouTube link, so you should have access to the recording from the last week, and then you can go through all these steps much slower. So I just had to go through them very fast now. Okay, now let's try to build the model. Okay. Now I'm slowing down, all right? If you guys have the file in front of you, if you already had the data sets as I ran those cells, if you ran those cells, you have a clean, ready, available data set in front of you. Now, I'm just going to go through a very standard way of, a simple standard way of building a machine learning pipeline. Again, there is nothing really mysterious here. I'm just using sklearn library and then adding each step one after another to create a machine learning pipeline. For those who are new into, and then my assumption is we are new into this. If you already did this work before, created machine learning pipelines, again, this is going to be very simple for you. Okay, so first of all, what I'm gonna do is I'm gonna define three things from my data sets. I'm going to say I'm going to treat some of the variables as numerical features. So what is numerical feature? I tried to explain earlier. A numerical feature is going to take many different unique values. For example, age. If you look at age, age is going to be taking maybe 50 different values among your patients. If you look at weight, if you look at height or BMI or chair stand test or HGS, which is grip strength test. So these are numeric, these are numbers, continuous numbers, which may take many different unique values, all right? So they are not categories. So I'm not going to use weight as a category here. So you can turn weight into a category. For example, if the weight is above a certain threshold, you can call it overweight. If less than a certain threshold, you can call it not overweight. I don't know how to properly call it. Or height, tall or not tall, right? So you can certainly turn these variables into categories, but in our model, we are going to treat these variables as numerical features. So on the other hand, when I say categorical features like exercise, education, smoking, DM, and HD, so these are whether a patient has high tension or whether that this person had diabetes or not, right? So these are going to be categorical. What is the frequency of this person's exercise? What is the education level? Or what is the smoking status? Okay, has he been smoking or not? So we had more detailed data about smoking, but I just simplified it into whether the person is smoking or not. That's it. So you can make this a lot more like smoking. In the data set, we have smoking rarely, smoking 10 cigars a day, 20 cigars a day. So we have that detailed information about smoking, but I just turned it into smoking 1 or 0. That means whether the person is smoking or not smoking. See if, all right. Now we are going to, and then the very important variable. So these numerical and categorical features are actually the input to our model. Okay, so if a new patient appears, we are going to ask from this patient, or we are going to collect these variables, the values for these variables from that patient, so that we can predict whether that person has sarcopenia or not. So in other words, my goal in here is creating a model which is targeting to predict sarcopenia. That's why I'm going to call it sarcopenia, or because I changed the name into SARC, SARC as my target variable. So I'm going to use this variable to predict this target variable. Okay, so I have in literature we actually use capital X for features, and then small y for the target variable. So the reason why we use capital X in mathematics, right? We use capital letters for matrices, and the features, these features, the numeric features, imagine this as a big matrix. So age, weight are columns of this matrix, And people, each person, each subject is one row in that matrix. So I will have a matrix of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 columns, and maybe 1,000 rows. But target is just one column, right? It's a vector. So that's why I'm using small y. Okay. So this is just how we, if you say in rather than X, if you say Z, it doesn't matter, right? So it's just a letter, but in literature, we use capital X to denote features and small y to denote target variable. Okay, so we try to explain what makes a feature numerical or categorical, why we are grouping features as numerical or categorical. So I try to explain it. Now, let's learn how we can split our data by gender. Remember, I'm going to create a model for male and another model for female. By the way, if you guys have any questions, please feel free to post your question on Q&A so that I will not miss your question. If I know the answer, I'll try my best. Okay, so let's split our data into female and male. Again, this is my entire data set, DF. So from my data sets, I'm going to, let me go step by step here. So this is my entire data set. My data set has these columns. From these columns, I'm going to use gender. Okay, gender. So I'll go back here. And then I'm going to open a square bracket. Inside the square bracket, I'm going to insert gender. So what I'm doing now is I am only selecting gender column. So this is going to be one, we call this one column of the data frame. Okay. So I'm just curious if this gender is 0 or 1. If it is 0, it's female. If it is 1, it's male. Okay. So that's what, as you said, the first 5 and last 5, actually in this data set, gender has the majority in this data set. So I have 5, the first 5 patients are actually female. The last 5 patients are also female. So you can look at the first 20. Let's see. You see there are some ones here. So these are the male patients. Okay. So next, after I get this gender column, I'm just going to create a Boolean column. So I'm going to turn this column into a column with only taking Boolean variables. So what does that mean? I'm just saying if gender is gender column or is an entry on in this column is 0 or not. Okay, that's what I'm doing. So if it is true, that means this is an entry which equals to 0. If it is false, that means it is not 0. Then I'm going to put this. When I say this, it's a column of Boolean values, true or false values. Again, true indicates gender is 0. False indicates gender is not 0. Now I'm going to insert this into my data frame, which is going to now only select data points from my data set where gender is 0. So as you see in the first row, gender is 0. In the second row, gender is 0. So I only chose the data points where gender is 0. Okay, all other data points are excluded. So this is going to be actually my female data frame. Okay. So let me copy this and then put it here. Okay, so these are the female patients. I'm going to do the same thing for male patients. Okay, so this time gender is going to be 1. As you see now, I split my data to male and female. Okay, let me run this. So next, what I'm going to do is I'm going to split my female data into feature set and target. Remember, capital X was representing features, small y is representing the target. So I already did that for female. So let's do the same thing for male as an exercise together. Okay, so this is going to be X male. Okay, so what is X? Remember, X is all the columns here, like age, gender, weight, height, all the columns. I'm not going to use ID. I'm not going to use ID in my predictive model because ID is not going to help predict anything, right? So age, gender, weight, height, these are all going to be part of my feature set, except this very last column, sarcopenia, because this is my target variable. This column is what I'm trying to predict, okay? So, and then again, remember, some of these columns are actually numerical. I call them numerical columns here, numeric features, and some of them are categorical features. So it doesn't matter. I'm going to take all numerical and categorical features, all of them together, and assign it to X male. Okay. So another thing is, let me show you this. It's not related to machine learning, but Python. So this is numeric features. Okay, so this is a numeric features. Probably I didn't run this one. Yeah, I need to run this one. Sorry. Let's run this cell if you had not run it. Okay, I didn't run this cell, so let's run this cell. Okay, so that I'm actually importing these libraries, and also I defined what numeric feature, categorical feature, and target means. Show this. Okay. Now, yeah, here. So when I say numeric features, so these are the numeric features. When I say categorical features, these are the categorical features. So when I say numeric features plus categorical features, I'm actually creating a new list from two lists. So this is numeric features list. This is the list of categorical features. When I sum up two lists, it's going to give me a one list of both numeric and categorical features. Okay. So the next thing is I'm going to select from my data set. Remember, this is my male data set here. This is my male data set. From this data set, I'm going to select both numeric features and categorical features. Okay, so this is the first thing I'm going to select. So let's do this. I created my feature set for male. Okay, so let me run this for female as well because I'm going to use it. All right. Okay, now next, as I did for female, I'm going to create my target variable for male. Again, from my male data set, I will only select the target column. And what is target? I already defined what target is. Target is sarcopenia. Okay. Okay. I'm going to select this target column. I'm going to call it Y male. Okay. That means this is the Y variable for the male patients. Okay. So let's run this. Now I created, and then it gave me an error. Oh, this should be from DF mail, right? From DF. Because I already created X mail already excluded sarcopenia. So that's why it couldn't find target in the sarcopenia. So this should be from the DF mail, which is this data set. Okay, which is this data set. From DF mail, I'm going to select target variable and assign it to Y mail. Let me run this. Okay. So I have X mail and Y mail. All right, good. So I created my data set. The next thing is I'm going to train a machine learning model. When I train a machine learning model, I want to do two things. Okay, I'm going to write it. So train a model, and second, test that model to see how well that model is doing. Right? So this is what I want to do. I want to train a model. Then this training a model is not going to guarantee that the model is going to work properly when I use that model for a new patient. So how do I know whether this model is going to work well when I receive a new patient? Because when I train a model, I'm using the available data set, right? So then I have a model which is not actually used for new data points. So how do I know that this model is going to do well on these new data points? For that, I need to test my model. So to train my model and to test my model, I need data set. To train and test, we need data set. Okay. So then next question is, when you test your model, how do you know if your model did correctly or not? Okay, so let's say there is this new patient and you are testing your model. How do you know if your model correctly classified this new data point into sarcopenia or not sarcopenia? How do you know that your model is doing this classification correctly, right? So because of that, when you test, your test data must also have the labels. So what does that mean? So that means if I'm going to test my model, the test data set should come with correct labels. So I have the correct labels. For example, there is this new guy, X new. Okay, this is a new patient. Let's call this new patient. Okay, so I'm going to put this new patient into my model. So this is my model. So I put my new patient into my model. The model tells me that this person has sarcopenia. Sarcopenia is one. Okay, so this is what the model tells me. Now, how do I know that this new patient has sarcopenia? I will only know that if this new patient somehow outside the model, in whatever the workflow I showed you at the very beginning, that workflow, like using the ultrasound images, using the BMI, creating a star score for this patient, and then using that star score to diagnose this patient with sarcopenia or not. So in whatever way, right now we are diagnosing patients with sarcopenia or not, that must have been done already. Okay. In other words, I know if this patient has sarcopenia or not. Let's say this new patient, the true label is sarcopenia equals 1. So what does that mean? This new patient, I know before I even put this new patient into my model, I know that this patient has sarcopenia. I know that. Okay. And then I put this patient to my model. The model also says sarcopenia. That means, so let's call this sarcopenia hat. Okay. That is my prediction. Let's call this prediction. And this is sarcopenia label. Okay. So this is what we in reality know about the patient. And this is what the prediction, what the model tells us in terms of prediction. If sarcopenia thread is the same with sarcopenia label, right? So this means our model correctly classified. Okay. So that's the idea behind having a test data set, right? So we need a test data set, and then that test data set comes with true labels, so that when I test a patient using my model, I'm going to receive this prediction, and then I'm just curious if this prediction is the same with the true label. If they are the same, then our model correctly classified. If they're not the same, that means our model is not correctly classified. So because of that, I'm going to turn my data set, in this case, my female data set, right? I'm going to split my female data set into train and test. So that's what I did here. So I'm going to do the same thing for my male patients. So X male, let me use the same X train male. Okay, all right, X train male. So this is going to be the part of my data set for male patients, which will be used for training purposes. And this will be the test. Okay. So again, remember, X is the feature set. In addition to feature sets, I also need the target variables. So Y train male, and then Y test male. Okay, so I'm splitting Y male. I'm splitting Y male to train and test, and I'm splitting X male to train and test. And by the way, both, if you pick a patient, pick any patient, I know the numeric and categorical features of that patient. I know that patient's label. Okay. So both the label and the features of the same patient should go into either train or test. So I cannot split Y. Okay. I cannot split Y male independently from X male. Okay. So in other words, a patient with his features and label go to either test or train data set. Okay. All right. So for splitting my data randomly, I'm going to do this randomly in this case, right? I need to split my patients randomly into train and test data set. I'm going to use this train test split, okay, function, or you can call it even class from sklearn's model selection library, okay, this one. So I already imported this train test split. So train test split is going to help me train test split is going to help me split my male data set. Okay. Another thing I'm gonna do here is, which I did for the female patients. I'm going to choose what size I want my test data set be. Okay. In this case, my test data set is 20% of my data set. In other words, when I split my data into train and test, 20% is test, 80% is training. So test size is 0.2. Okay. And another thing is, when I split my data, I will be splitting it randomly. So next time when I come back next time, and then when I want to run this, okay, so for any, is the same that we've been using through your sessions? Yes, yes, Jorge. So this is the same, what is that? Same notebook that I have been using. Sorry, I saw the question late. And for any model building, is it advisable to have numeric data values as numeric features and Boolean data types as, no. Okay, so this requires some explanation more than, so when you look at your data sets, if a variable is numeric, this doesn't mean that that variable has to be numeric. Okay, for example, I can categorize my patients in terms of their smoking habits. So I can assign smoking equals 0 means no smoking. Smoking equals 1 is smoking. Now 0 and 1 are numbers, right? But I'm not going to call this variable as numeric because I know that 0 and 1 are just two values, which is used for categorizing my variables, right? So that's why you shouldn't be like, if I check the data type of a variable, if the data type is integer, we shouldn't automatically assume that it's a numeric feature. So we should actually think about what unique values that variable is taking. And then if the number of unique values is very limited, again, based on the context, in this case, say smoking 0 or 1, both 0 and 1 are numbers, but of course, 0 and 1 are indicating two categories. They are not just numbers, they are categories actually. So that's why we cannot simply make our decision on which variable will be numeric or categorical based on the data type. So data type will help us identify numeric values, but we need to also look at the unique number of values each variable is taking, right? Okay, so yeah, I was talking about this part here, random state. So you have a number of data points. Okay, let's say you have 1100 data points, okay? So this is your total number of data points, DF, male and female, okay? So there are this many data points. Now you use this train, test, split, okay? You are splitting your data set, right? So what happens is when you, when you split your data into train and test, what happens is I take these 1100 data points and randomly I assign these data points to train and or test sets. Okay, so some of the data points will be randomly find themselves in the training data set, some of them will find themselves in the test data set. So this happens randomly, and this randomization is important. Otherwise, you may have introducing biases into your model, right? So you need to randomly assign. What if you assign all easy cases to test data set, right? If you assign all the easy cases to test data set, your model is going to look like very successful at the end. Okay, so we make these assignments to train and test data sets randomly. When you come next time, let's say last week we did this, and this week we are again working together. Because this time the train and test data sets, again, every time they are assigned randomly, if I want to get the same assignments as I did last time, okay, even though this is happening randomly, those randomly assigned data points, I want to find the same data points in train and test data set every time I run this randomization. So for that, I'm going to set this random state parameter, okay, to some value, 42 in this case, or 0 or 1, doesn't matter. But what happens is when I set this random state to a specific number, every time I run this line here, the same data points will be in the train data set randomly. The same data points will be in the test data set randomly. We can talk more about how random numbers are being generated. But just for information, random state makes sure that your experiment can be repeated. Your experiment can be repeated. Otherwise, if I get different data points in train and test data set every time I run this, so the differences I see in the model performance, you can say, oh, This time model performance is different because data points in the train and test data sets were different, right? So you may make this claim. To make your experiment scientific and then that you can repeat it multiple times. So we are going to use this random state set to some certain value. Okay, now let's continue. So it means not just so if you want to make representations of category variable more sensitive, what type of encoding? So again, at the end, okay, at the end, let's say you decided that a variable is going to be a categorical variable, then you are going to turn its data type into, say, object, okay? So it can be a string. So that's going to make your job easier. So now you know that it is not a number anymore. 0 or 1 are just two strings. They're not numbers. So you can use them as categorical variables if they're binary. If they're not binary, so for any numeric feature, what I do is in general, I turn their data type into string so that at the end, I can split my data into numeric or non-numeric by just checking their data type. If data type is object, it's categorical. If not object, then it's numeric. It's going to be a lot easier for me to assign variables into these two groups by just checking their data types at the end. Okay, so let's continue. And then I'm going to set this random state to can 42. Okay, so I split my data, female data set, and then I split my male data set into train and test. Okay, anything else here? So I split my data by gender. I train and test it for females, and I did the same thing for males. All right, now I'm ready to start creating a pipeline for pre-processing. So this part is a lot longer than how it looks like, okay? Again, this is a very simple machine learning pipeline, guys. Anyone who did this before will immediately see that it's very simple. Is there any rationale to choose test size 20%? In general, we use 20, 80%, 25, 75 by default. If you don't say anything about test size, it's going to be 25%. If your data set is very large, you can use 90 to 10%. So, but 20, 80% is in general is used in literature, right? So out of every 5 data points, 4 of them are trained, 1 of them is test data set. If you have a really large data set, then you can split to 90 to 10%. 10% will be test data set. There is no really set rule on what this percentage should be, but in general, we use 20, 80% split. Because we need data points to train the data set. So I need to use majority of my data points for training purposes. That's the most important part. So testing is just so when you test something, right? So you cannot exhaust all possibilities, right? There is always this possibility that there are things that you didn't test. So it's okay. But for training purposes, I need as many data points as required. So that's why I use majority of my data points for training purposes. Okay. So now I have numerical and categorical features. Okay, features. Okay. So there are a couple of things I will remember. I already cleaned the data set, right? I already did that part earlier. I already cleaned the data set. Now I'm going to pre-process data set further. So this cleaning the data set is also part of pre-processing, but I'm going to pre-process my data set further. So what does that mean? So imagine that you are building a model, yeah, and then in your model, so there are 2 features, okay, and then I'm going to go to a different domain just for this example, okay. Let's say you are predicting house price, okay, and then house price is a function of let's say square footage. I'm going to use SQF, okay, and room numbers, okay. I'm going to use room number, okay, room. So let's say you know these 2 things to predict house price, right? And you're building some model. I'm not going to talk about what model you are using. All right. And then square footage is going to be in terms of very big numbers. and number of rooms is going to be in terms of, let's say, numbers from 1 to 10, let's say. So just because square footage has very large values and just because room is taking from a small range of small values doesn't mean that square footage is much more important than room numbers, right? So they both are very important variables to predict house price. So because of this huge difference in terms of range of values these two variables are taking, so you may think about scaling your data set. Now, scaling means I'm going to bring these two variables down to the same range of values. Okay, again, let's not talk about details of that. It's one full lecture, scaling, right? Okay, I mean, scaling and plus something. I will use half of the lecture on scaling. Okay, so scaling may not be required for all models. Okay, for example, if you train a decision tree model, maybe scaling doesn't matter. Okay, but here I just put it as an example so that you know that you may need to make some transformations on your data points, and different transformations should be made on different variables. For example, if your variable is numerical feature, then scaling is going to be one option. Okay, but you're not going to scale any categorical feature. What are you going to scale, right, when it is categorical feature? So for categorical features, let's say, again, let's go back to our data set. So in your categorical feature, you have smoking. So smoking is taking values like 0, 1, 2, and 3, let's say. So what does that mean? Actually, smoking is not just taking 0 and 1. Let's say education. Okay. So what does that mean? Education 3, 0, 1, 2. So if you intelligently classified your education to like illiterate is 0, university is 3, then still this makes sense, right? 3 is bigger than 0. But most of the time when we have categorical variables, we are not going to have this order, right, in the numbers. So in other words, 3 is just some number that you are using to categorize a certain category, right? So for example, 3 is a group, and 2 is another group, 1 is another group, 0 is another group. So then I need to encode these categories, right? So again, 0 can be illiterate, right? Or 1 can be, what is that? Primary school. And then 2 can be high school. So let's go this way. Okay. Then how am I going to let my machine learning model know what is this and what is that and what is this? So how can I differentiate between these three when I have a new patient coming and then I'm going to introduce this patient into my model? How am I going to let my model know what is illiterate, what is primary? So what we do is, let's say there is this new patient. Okay. And then this patient is high school. So then this new patient, okay, will take a 0 value for illiterate. Okay, it's going to take a 0 value for illiterate. Primary will take a 0 value, but high school will take a value of 1. Okay, so this new patient is encoded into 0, 0, 1. That means this person is not illiterate, this person is not primary, this person is high school. Another patient comes primary, then that person will take 0 value for illiterate, 1 value for primary, 0 value for high school. This is called one-hot encoding. Okay, so or creating dummy variables. Or categorical features. So what we are doing here is, given the type of the variable in your data set, I'm going to transform those variables into a new variable by using, let's say, scaling on numerical features and maybe one-hot encoding on your categorical features. In other words, I'm transforming my data set. Okay, when I transform my data set, I'm going to transform my numerical features differently, categorical features differently. And there is a reason why I'm transforming. It's It's a long discussion maybe, but there is a reason why I am transforming my data points. And I need to do these transformations happening one way on numerical features, in another way on categorical features, right? So that's what I'm doing here. Okay? This is what I'm doing here. Probably you need to sit down and then actually, if you don't know what this is doing, so maybe we need to study this a little bit. But here, what happens is I'm creating a transformers pipeline for my features. So I have, remember, numerical features. Remember, I have categorical features. So on my numerical features, which are these guys, these variables which are taking numbers, numeric values. So I am going to scale them down. Okay, again, for this model, we don't need to do this for information, but I'm just introducing this so that we know that we can transform numerical categorical features different. Okay, scaling will be done on these numerical features. On the categorical features, again, which are the features which are taking a limited number of unique values like exercise, education, smoking. So I'm going to transform them using one-hot encoder. So this scalar one-hot encoder are actually two transformations available, which I already imported them from sklearn, and they are part of the preprocessing. So we are still continuing with preprocessing our data set. Okay, I cleaned my data set, but still my data set is not ready to be trained. I am preprocessing my data set. Okay, here it is now. Look, guys, so this is your raw data. Okay, you get your raw data, then you clean your data, and then we discuss what cleaning means, and then you create a pipeline of transformers for your clean data. Okay, and then you create a pipeline of so I'm going to call this like this clean data. This create a pipeline of transformers for your clean data set. I'm going to call this preprocessing. Preprocessing. Okay. And then next, you create a pipeline of preprocessing and training, model training. So this is the general workflow when we receive the data set and then when we want to train a model. We clean our data sets and then we create a pipeline of transformers. When I say pipeline of transformers, when I put my data set into this preprocessor, my data set is going to be split into numerical and categorical features. On the numerical features, my data set will be scaled. For the categorical features, my data set is going to assigned with these dummy variables. Like for each category, I'm going to receive a code of 0 or 1. Okay, so once I go through this preprocessor, I'm going to put this preprocessor and my model training phases, but I'm going to put these two into a pipeline, and that will be the last step to create and train a model. Okay, so this is where this is what I'm doing here. So this preprocessor is what I defined earlier here, this one. Okay, what does this preprocessor does is it is transforming my numerical and categorical features. Then following this preprocessor, I introduce my model. In this case, my model is gradient boosting. There are so many different models. For this case, I chose gradient boosting algorithm. So let me give a pause here. Let's see. Yeah, capital H, S, and then small capital H and S are different strings. Yeah. Okay. All right. So yeah, illiterate was thank you, Randa. So I was writing this incorrectly. Okay, let's do the gradient boosting classifier pipeline together, and then it is almost time for us to stop. But let's create this pipeline for the male patients and then leave it there. Jorge is asking from where I take the validation data. Jorge, what happens is you take the full data set, you split the data set into train and test, and then you take the train data set, you split it further into train and validation data set. So that way you're going to have three-way split. And most of the time, so you can automate this validation dataset creation step. You can automate this. You don't need to create it yourself. So most of the time, these libraries are taking care of it. Okay, guys, let's create this pipeline for the male patients and then train the model and then leave it there. Okay. So what I'm gonna call this is pipeline. Write it here. Pipeline male. Okay, so this is the pipeline for my male patients. So I'm gonna use the capital P pipeline. Okay, this is coming from sklearn. I already imported it. It's basically, it helps me create a pipeline of steps. The first step is going to be my preprocessing step. Okay, I know this is too much for if you are totally new, it's too much, and then I'm having difficulty with explaining things thoroughly. But let's do this together for once, and if this is something new to you, you can explore this further. So this is a pipeline which is composed of steps, and then these steps are actually a list of things. So those things are the steps in my pipeline. Okay, so my data is going to go through the first step, and this first step is defined as a tuple. This tuple has two elements. The first one is the name. Okay, I'm gonna call this preprocessor. Okay, like this. So I can even call this preprocessor male, but let's call it preprocessor for now. Okay, and then preprocessor. So this is the special name I give to this preprocessor. What is preprocessor? It's another pipeline which I created earlier. It's a column transformer pipeline I created earlier. What this preprocessor does is it takes the data set, it splits data into numerical and categorical features, it transforms numerical features differently, categorical features differently. All right. So in my pipeline, the first step is preprocessor. Now the second step is, I'm going to go to the next slide, another tuple. The second step is the model itself. I'm going to call this classifier. So then this is the name of the model. I'm now typing the model itself. This is gradient boosting classifier. Okay, so this same model I'm using for the female. Again, there's so much to do here after you come up with this model, and then the question is why this model but not the other one? You need to test this for many different models as well. Again, this is just one example. I'm just going to copy this. These are the model parameters and put it here. Okay, now we created the pipeline for the male patients. Again, my male patients data set will go through the preprocessor first, and then will be fit to this model. This model will be trained on that preprocessed data set. Let me run this. Then need to run this first, this one first. Need to run this one first, and then run this for female and then for male. So let's look how that preprocessor looks like. Okay, so this is the preprocessor. Look, this is how it looks like. Okay, so your data set is going to get into this transformer. The numerical ones will be going through this transformation. Categorical ones will be going through that transformation. Let's see how your pipeline looks like. And then I'm going to stop after this one. Pipeline. Okay, now your data set will get into this pipeline. Numerical ones will be split. The data set will be split into numerical and categorical. Numerical ones will be transformed using this transformation. Categorical ones will be transformed using one-hot encoder. Then those transformed columns will be concatenated, and then they are going to be used for training this model. So this is a pipeline. You drop the data set from top of the pipeline. At the end, you receive a trained model, right? Okay. I mean, I know. So there's so much, a lot of things that very quickly I just mentioned. So next step is after you train the model, the next step is you evaluate your model. So again, I put the example for female. You can do the same thing for male patients. And then here, I just wanted to let you know that, hey, gradient boosting is one model. How about random forest? Okay, so you can actually, that's what you need to do. You may try multiple models, get one benchmark model, and try to beat that model with some other model. If you can get a better result with some other model, then switch to that model. Okay, And then here is the model. Based on the model I picked, how each variable is actually contributing to the predictive power of that model. For example, age in this case is very strong indicator of whether a person is going to develop sarcopenia. Chair stand test or grip strength test or BMI, right? So if you know these variables, more or less, you're going to know whether this person has sarcopenia or not. Okay, that's what it means. And I put this step here, which is very important for medical applications, model calibration. So I think I put some explanation here. No, I didn't put. Yeah, here. Yeah, imagine that you developed a model, and then your model is predicting a 90% probability of having the disease, let's say sarcopenia. So then if that is the prediction, 90% probability, you would expect 90 out of 100 patients will actually have that disease, right? So if that is the prediction. But most machine learning models are not going to give you this kind of a. So here it is. Here's what's going to happen. Let's say for this model, the model is going to tell you if a patient has 90% has or less probability, that patient does not have sarcopenia. Okay? Actually, in my model, this was 95%. So what does that mean? This is a very misleading result, right? So anyone who's using this model will not be able to interpret this if they don't know what's going on here, right? So what model tells me is that this is what the model told me when I first trained the model. If a patient has 95% or less probability, then that patient doesn't have sarcopenia. How do I know that? Because I checked the model results. All the patients above 95% have sarcopenia, below 95% doesn't have sarcopenia. But I mean, what this tells me is 95% probability. It actually tells me is if I have 100 patients, 95 of them, if I have, let's say, what is that, 100 patients, and then if the probability is coming 95%, if I'm new into this model, I'm just using this model. So I would think that 95% is, too high. So anybody who's above 50%, anybody who's above 60% should also have sarcopenia, right? But here it says if the patient has 95% probability, according to this model, then you can only say this person has sarcopenia. So this is not reflecting the ratio of patients who actually have sarcopenia. So in other words, out of all the patients whose probability is, let's say, 90%, okay, all the patients. So when I tell you this, what you understand is out of all the patients whose probability is 90%, that means these patients whose probability is 90%, 90 of them are going to have sarcopenia. That's what it means. Okay, I'm repeating. If I have 100 patients and these 100 patients have a probability of 90% sarcopenia, that means 90 of these 100 people actually have sarcopenia, right? So that's what the model tells me. But according to my model performance, I'm saying that a patient will be diagnosed with sarcopenia only if the probability is above 95%. So in other words, if the probability is 90%, I'm going to diagnose that, predict that that person doesn't have sarcopenia. So this model needs calibration because these probabilities are not reflecting true distribution of the disease in the patient population. Okay, so that's why most of the time maybe we may not know this calibration step is so useful, but for application purposes, after we develop the model, we test the model, we decide on which model we're going to use, we are going to calibrate the model so that the application can be used with some meaningful results. Like when I say 90% probability, that means anyone who has 90% probability, 90 out of those 100 patients have sarcopenia. That's what it means. But in this case, without calibration, Out of 100 patients with 90% probability, maybe 1 or 2 of them will have sarcopenia, which doesn't make sense. Okay, I will stop here. Sorry, so it was very fast. Maybe we didn't cover everything that I planned, but that's all for today, guys. I'm already beyond the time limit. So see you next time in other workshops. I already shared the data set. I already shared. Actually, I have another file, the day 2 of this one. Okay, so you can check that file too. It is already in this folder. So I didn't even have time to cover day 2. Okay, with day 2, actually, I am now trying to improve the performance of the model. Okay, so that's what I was trying to do here. Again, you can and then test the model, comparing it with the current workflow. So you can check the second data file yourself. And then again, thank you. I'll see you guys next time. Okay, bye. Another seminar. Yeah, we're gonna have more seminars, but about this topic, we haven't scheduled a third one about this topic. I think this will be the last one. Yeah, Alessio. But we're gonna have more seminars, more workshops coming, definitely. Okay, thank you very much for listening. Take care, guys. Thanks. Yeah, for AI in medicine, we'll have more workshops coming. Thank you.